Dr. Amit Shaw, who has taken off his time from his busy schedule to be here with us to share his experiences on a very interesting topic. I'm sure that many of you would be, eager to wait for this presentation. In fact, we have Dr. Amit Shah from IIT Kharagpur. So before I go to the speaker, let me also just share a few words on what we have been doing over the last few days. In fact, we have been having this series of webinars, and I'm sure that many of you would have also seen the webinars which are already there on the Facebook Live as well as on the YouTube. And we have covered a host of topics ranging from cement, concrete, smart cities, reinforcement detailing, geotechnical engineering, and the perspectives given by different speakers would be useful for us to look at each topic from a very objective perspective. And I am sure that when we look at each of these challenges from both theoretical as well as practical perspective, we get a lot of solutions for it. Ramco Cements, as all of you know, is an organization which has been there in the Indian cement industry since the 1960s, and we have been able to introduce latest technology in cement manufacturing process, and we have also got number of awards for sustainable development in terms of reducing the emissions from the cement this thing by virtue of introducing the latest technology. And we have also the surface miners, the vertical rollers mill, which enables us to have a cement with proper particle size distribution. So a lot of initiatives which have been taking place in the Indian cement manufacturing process, whatever developments has been taking place, we have been able to incorporate. And one of the main thing that we have been doing in the recent past is trying to understand, what the customer wants, what kind of concrete he is making. And in that process, what has happened is that we have been able to customize the cement based on the concrete requirements. And we already have 12 brands of cement. Ramco Cements is there. And these 12 brands of cement, you will find that the types of cement which can be classified is we have the Portland Pozzolana cement, we have the Portland slag cement, we have the ordinary Portland cement, we have the SRC cement, and we have the Ramco Superfast, which is specifically for precast applications. Now within PPC, we have four brand of Ramco cement. We have the Ramco Supercrete, we have the Ramco Superfine, Ramco Super Grade, and we have the Karthik cement. So the thing is that we have these four types of cement, and Ramco Supercrete cement and Ramco Superfine cement is specifically meant for concreting. And then we have the ordinary Portland cement, OPC 43 grade, 53 grade, 43 grade infra, and 53 grade infra. Infra cement has been particularly customized for concrete with a longer slump retention time, because many of the RMC units who are using, they mix this blending material at site and they need to have longer slump retention time. So we have taken that into account, and that has been made possible there. And of course, precast application needs a separate cement, because by virtue of they have to remove the mold within a quicker time, and they need to have more number of blocks per bag. Then the paving block, as we all know, they need to manufacture a paving block with minimum edge breakage and all that. So we have been able to take into account, and we have been able to give them Ramco Super Fast cement, which is specifically meant for precast applications. So these are the types of cement which has been manufactured, and we also have our research and development center. I would request all the construction professionals, those who have logged in, to make use of the mixed designs that we have done using our cement with various types of admixtures, admixture A, admixture B, admixture C. Each of these admixtures may behave differently with our cement, because as all of us know, cement admixture compatibility has a lot of other factors also. So we have been able to do the trials, and we have got some data bank of the concrete mixed design that we have done for various projects, for various consultants, which could be of use to many of you. So you could always share, we could always share that with you, provided you give us what concrete grade you need. So what is more important is that each customer must define the properties of concrete that they need, whether it is in terms of grade, whether it is in terms of slump retention, and various parameters. Like say, for example, durability parameters are also there. We have the RCPT test, we have the DIN water permeability test, which is there. Those equipments are there at our research center, which helps us to evaluate the durability of concrete, which is also a very important property as far as concrete goes. Many of these durability tests are not being done in many of the construction sites, because we only are happy with the compressive strength or slump retention for that matter, but durability also can be measured, and that is what is very important. I am sure that many of the projects would also would want to have a concrete with higher durability, because longer life is what is one looks at. So as far as today's topic is concerned, let me just introduce the speaker of the day, Dr. Amit Shaw, who has joined us. In fact, he He is an associate professor from the Department of Civil Engineering, IIT Kharagpur. He completed his BE from IIEST Shivpur, MTech from IIT Roorkee, and PhD from Indian Institute of Science, Bangalore. He was a research fellow at University of Aberdeen, UK. Prior to teaching, he had worked in responsible positions in major construction firms like Gammon India Limited, L&T's ECC division. His research interest includes impact mechanics, particle-based methods. His research papers have been published in various journals, international journals of solids and structures, computer methods in applied mechanics and engineering, computer modeling in engineering and sciences. He was awarded Young Faculty Award 2012, Indian Institute of Technology, Kharagpur. So we in fact have been privileged to have many experts from IIT Madras. We had IIT Kharagpur also we had. Now we have Dr. Amit Shaw also from IIT Kharagpur. IIT Delhi we had Dr. Bhattacharya who had spoken on concrete. So in fact the presentation which has been given by various speakers, I am sure would go a long way in enhancing the knowledge of construction professionals. So with those few words, let me invite once again Dr. Amit Shaw. Over to you, sir, for your presentation, and thanks for joining us. Thank you so much.
Thank you, Pillai, for your and it is good that you have been organizing this kind of national webinar series on various aspects of civil engineering. It's really an honor to be part of it, and many thanks for giving me the opportunity to showcase my work. Without wasting much of time, let me just greatly focus on the topic of the presentation today. As you can see, this is mesh methods beyond classical modeling techniques in structural engineering. I have been working on this topic for quite some time, and whenever we talk about analysis technique, we all are familiar with the direct stiffness method. We all are familiar with finite element method. So what we'll do today is we'll try to see, is there anything beyond those classical techniques which are very well known? And if there is something beyond that, then what is the motivation to explore the possibilities, and what are the areas where those modeling techniques can be useful? So these are the things that we'll be covering in this topic. Okay, we checked yesterday and just before the presentation also about the bandwidth. So what I prefer is we may find some difficulty in between because of the bandwidth. So I'll just put my video off so that we can conduct the entire presentation very smoothly. Okay, so first thing first, these are the whatever I'll be presenting here. These are the work of my research scholars. These are the research scholars. Some of them already defended their thesis and are in different positions in different IITs and different other universities. And some other research scholars are working on various aspects of this method, and I'll be presenting some of their work. Well, let us first understand what is role of an engineer, or specifically see at the end of the day, we have to build something. We have to build some structure, right? Now, when we say that we have to build some structure, it is just not one-step job. There are various steps to be followed before the building is realized. Before you construct a structure, there are many steps. It starts with planning of the structure, architecture model, then analysis, architect design, drawing, and then execution. So one of the important steps in the entire process is analysis, right? And what is analysis? Analysis is essentially checking the feasibility of a structure. If a structure is subjected to different circumstances, then through the analysis we come to know in how that structure under different loading scenario may respond. And that understanding, with that understanding, we go on to design a particular structure. Now, in engineering analysis, there are different steps followed. First, we have a physical system. Physical system is the structure itself, the actual structure that needs to be done. Okay. Now, we don't work on a physical system as it is. We need to idealize the system. For instance, when we talk about truss, frame, or beam or column, these are all some structural idealization of some three-dimensional structure. We idealize so that we can put them in a computational framework or in an analysis framework, which we know. So from the physical system, you have to idealize the system. You have to make this, you have to simplify the system, right? Now, once the structure is simplified, the system is simplified to write, we express, represent the system through some mathematical model. And once we have that model, then we need to find a solution of that model. Now, just put that in a better perspective. Let me give you the example of that. So, when we talk about analysis, analysis is essentially the last three steps: idealization, mathematical, idealization, solution. So, this is the starting point. Idealized structure is the starting point of analysis. We always start analysis on beam. We know how to analyze a plate. We know how to analyze a frame. These are all idealization of some physical system. Let me give you an example of that. So this is an example. Suppose the physical system is, say in this case, a dam. Then we have an idealized system, the computation model of the dam. And then once the system is idealized, then we represent the system to some mathematical model. In this case, it is the equilibrium equation with some boundary conditions and initial condition. And then with this boundary problem, when we solve this boundary problem, we get the response of the structure. Response of the structure is one of the information in various points, what the stresses, strain, those information we get from the analysis. Now the important point is when we go from in this flow from the physical system to the solution of the system, at every stage we make some assumptions. We make some assumptions. So when we write the computation model like this, we assume that in this case at least, the dam is a plane strain problem. Okay, so this is an assumption. Again, from computation model, when we write mathematical model, we make some assumption about the boundary conditions. We make assumptions about some material property. We make assumption. For instance, concrete. If you look at a mesoscale, concrete is a heterogeneous material, but most of the time we assume concrete is a homogeneous material. So these are all assumptions. Now again, from mathematical model, when we solve the mathematical model, we also make some assumptions. We discretize the entire domain, discretize the equations, okay, and then get the solution. Now, why I'm continuously stressing on the term assumption? Because assumptions are the limitations of a model, of a analysis framework. Every analysis framework is based on certain assumption, and these assumptions are essentially the limitations. Wherever these assumptions are not applicable, in those cases, those analysis framework cannot be applied. In every assumption, we slightly deviate from the physical system. When we from the physical system, when we represent the physical system in the second computation model, we make some assumption, and with those assumptions, we slightly deviate from the actual system. Again, from computation model, we present the computation equations based on some assumptions. With that assumption, we further deviate from the physical system. So therefore, always we work on a representation of the actual system, a close representation of the actual system. And therefore, in this context, let me, okay. Now, there are several modeling, several analysis techniques available in the literature. All the analysis divide broadly in two parts. One is methods which rely on mesh, finite element method, and then the counterpart of that, the method which does not rely on mesh, that is called mesh-free method. And the focus of this presentation is that. Now, so what I will, in the presentation, what we'll do is that we'll try to address three questions: that why mesh-free method, what is mesh-free method, how mesh-free method. Why mesh-free method? We will try to find out sufficient reason to explore this field. We try to find out what are the difficulties associated with mesh-based method, and then with the difficulties, what are the limitations that for a particular problem we may have when we try to get the solution. Now, when we understand the motivation of the mesh method, when we convince ourselves the sufficient reason why to study mesh method, then we'll see what is mesh method, how discretization takes place in mesh method, how to solve this Gammon equation, and then finally how mesh method, the implementation issues, and then followed by some examples. Okay. So let us see why mesh methods. Okay, before that, now let me show you some videos. For instance, before that, as I was telling you, with every assumption we slightly deviate from the physical system. So it is really then, it's an irrelevant question whether a model is accurate or not. The very word model itself means it is not accurate. It is not exact representation of the physical system. The question we should ask whenever we try to use any analysis framework, whenever we try to use any modeling technique, the question we should not ask whether the modeling technique is right or wrong, but rather we should ask whether the modeling technique is useful or not for a particular context. Okay, so all models are essentially wrong, but some are useful, and we try to find out, and we try to use only those methods, those modeling techniques which are useful for the given context. Okay. Now, to understand the motivation of mesh method through some practical example. Now, suppose I want to study structure under blast loading. I want to design structure under blast loading. So before we do so, we need to understand how a structure may respond when it is subjected to blast, right? Now, I tried to model it, the entire blast loading, or my student tried to model it, the entire structure under blast loading using LS-DYNA software. Now, I'll just give you what kind of behavior we observed from the analysis. So I'm going to play a video. Yes, I see this video. So this is a bridge. Okay. Now we have taken just a small bridge, simply supported bridge, and then we have put some explosive just below the deck, and then the explosion takes place. Now, what we'll observe now in this video, that after the explosion, how the damage structure and initiates in the structure, and how the damage propagates. And when the damage propagates, what happens to the structure? So yeah, see, these are the damages. These are the damage starts from here. Again, this initiation location of the damage depends on the position of the explosive, standard distance, intensity of the explosive. But for all these, for the given choice of parameter, in this case, the damage starts here and then it propagates, and you can see how it propagates. You can see all these dots. You can see the yellow dots, and these are essentially fragmented part of concrete. Okay, and then if you can see some lines in this, those lines, you can see these lines. These lines are essentially the reinforcements. Okay. These are the reinforcements. So you can see this is the way the structure actually responds. Now this is how this simulation will come towards the end of this presentation. But then the point I want to make is, whenever this kind of behavior, the methods which relies on mesh, they have a limitation. Limitation in the sense, you see, when discussing, if I believe that you all are familiar with finite element method. Just if you recall what process we follow in finite element, we have a domain, a structure, we discretize into elements. Okay, now but the elements are connected together at the nodes. Now they remain connected together at the nodes. We do not allow the separation of this element in the classical form of classical finite element formulation, okay, standard finite element formulation. But then when this kind of fragmentation takes place, this kind of failure takes place, then you really you do not have luxury to make the connected between the elements. The element, there has to be a separation between elements. You have to model the computational framework, the analysis framework used that must allow separation of those elements. Otherwise, you cannot model the structure. Fragmentation you cannot model. But then the method based on elements really cannot do so. They can do model to some extent with some additional enrichment. We'll come to that point as well. But by and large, it is very difficult to model this kind of behavior using finite element method or methods which rely on mesh. And there are many such examples wherever you have crack propagation takes place, wherever you have a fracture, fragmentation, everywhere you cannot model it. Okay, let me show you another example. Another example is, take this example. Okay, what is this example? This example is a plate which is subjected by impact of a sphere, of a ball, with a very high speed. Okay, in this simulation, the speed is 3.1 kilometer per second. Now, so this is how the deformation pattern. Okay, now I'll show you if I zoom in at some point. See here, if I zoom in, then you will see what happens to the elements at those points. Practical application of this kind of simulation will also okay. Now, so the point is, so in those places, it is difficult to use finite element method, and therefore we need a method which does not rely on elements. And then the choice is element-free method. Remove the element from the formulation, or remove the mesh from the formulation, it becomes mesh-free method. That is the topic of this lecture. Okay, so suppose I want to model it. This is the physical system, actual structure and actual blast. And then, as I said, the analysis step is we have a physical system, then we need to idealize the system. Now, this is the idealization of the system. This is the structure, and this is the explosive. And then after the explosion, the shock wave generates, and the shock wave propagates through air and heat the structure, and then the medium is here. So this is our system. Okay. Now there are many ways you can understand this system. I'm just going to give you some examples of that. Suppose I want to analyze this system. How the possible ways we can analyze some examples. The first idealization is just model the structure. Whatever, depending on the explosion, depending on the intensity of the explosion, depending on the standard distance from the structure, what eventually happens, eventually shockwave generates an exact pressure on the structure, right? So if you can calculate that pressure as a function of elements of this explosive, then do not model the explosive and air, just model only the structure and apply pressure on the structure. So this is one technique. You model just the first one, model only the structure and apply pressure on the air. The second idea, another idealization would be you model structure, air as well as explosive. So you model explosive with something, allow explosion to happen, allow shock wave to generate, and then allow the shock wave, model air and allow shock wave to propagate through air, and then eventually the shock wave hit the structure and then get the response of the structure. So either you can model only the structure and apply pressure on it, or we can model the entire, we can idealize the entire system, explosion, air, and the structure all together, and then do this simulation. But again, what idealization to follow, it also depends on what kind of response we are looking for. And based on that, whether a particular idealization is useful in that context or not, based on that, we need to idealize. Right. Now, this is finite element. Now, finite element discretization. All this entire structure is discretized with elements, and when we tried to analyze the structure under blast coding, we had a problem. We could not model it. The simulation I showed you, that is not just finite element. There is another method we use. I'll come to that point as I say. But when we tried to model only with finite element method, it was very difficult to model. Now, other examples. Okay, see the examples what I am showing from my interest, but you can correlate the similar kind of problem to many other fields as well. For instance, the armor we use for military vehicles. So these armors are subjected to impact of bullets and blast loading. So whenever this bullet come and hits the armor, then there is a fragmentation in the armor, failure takes place. Again, if I want to model it for the design of armor, if I want to model it, then I have to analyze it. I have to do the simulation. But when we try to do the simulation, the classical methods, which relies on mesh, is very difficult to be implemented in this context. This is another example. Again, you see the example is we as a human being is very popular or unpopular, whatever you may say, that polluting things, right? We have polluted our earth, and we are also in a process of polluting our space. Now, polluting our space means suppose we send some space vehicle and then some accident happens there, or we send an anti-satellite missile, destroy the satellite in space, and then what will happen? If a large object, they may come to Earth, or they may come to Earth atmosphere. Earth, or many small fragments, they do not come to Earth atmosphere. What they do, they orbit in low Earth orbit. You see, this is Earth and this is low Earth orbit, and these are the particles you can see. These are essentially the fragmented pieces of different of satellites. Okay, so these are called space debris. Okay. Space debris, why the space debris are important? Because you see, suppose if you want to send a satellite in space, and then if that satellite is hit by space debris, these space debris are very fine particle, and they are moving at around, say, just give an estimate, say 10 kilometers per second speed. So if with that speed, may actually may cause significant damage in the structure. So if we want to send a satellite, and then if that satellite is hit by a space debris, then considerable damage may occur. So when we model the movement of this satellite, we also need to keep in mind the environment, the debris environment, where there is a debris, at what speed they may come, what is the density of the debris, whether this area is safe or not. Those are the things we need to keep in mind. Otherwise, it will cause significant damage. Just for give you an example, it is not just few years back, an international space station was hit by a small debris, but luckily it was the solar panel which was hit by the debris. You can see a small white dot here, which is the damage caused by the debris. But as I said, luckily it was the solar panel. But had it been the actual structure, the main structure, then it would have been a disaster. So we need to. Another thing is, the question is how to understand how a structure responds. See, when we talk about a structure could be anything. It is not just a truss or a frame or a piece or a building. Anything which is made of small pieces and to serve certain purpose can be coined as a structure. So if I want to study how the structure, if there is an impact of debris on the structure, then how the structure would behave. That information is important, because if we have that information, then only we can design the structure. We can design the shield for the structure. Okay. So for that, numerical simulation is important. And then again, what methods do we have to numerically simulate it? If we go back, if we try to use finite or mesh-based method, then there is a limitation, as we have mentioned many times in the presentation. Then we have to find out an alternative technique. We have to, beyond these techniques which are available, these are mesh methods. So just this is an interesting experiment, as I was saying. With that speed, a small object, a tiny object may cause significant damage. It is, you see, there's a thick plate which is hit by a small sphere. You can see the diameter of the sphere as compared to the thickness of the sphere, and it was, if I recall, the speed was around 7 or 8 kilometers per second. The speed of the sphere. You can cross-check the exact velocity. But the point I want to make is, you see, with that speed, a small tiny object, and you see the crater formation. There's a huge crater formation caused by the small object. So just mass is not important. At what speed, with that high speed, even a small mass can cause significant damage. That's the reason why this impact of space debris is very important to study. So the second section I was talking about, a plate which is impacted by a sphere, is essentially the simulation of this problem. This is the plate, and this is hit by a small sphere. Okay. When we do this simulation, as I was saying, I will just zoom that part and then show you what problem is there. When you try to simulate it using element-based method, you see there's a huge distortion of elements occur. The elements get distorted severely. At these points. Okay. Now, when you have a severe distortion in the element, then in accuracy, we have some problem in this solution, because one of the premise in element-based formulation is element must satisfy certain criteria, certain geometric criteria. So if they are severely distorted, those criteria are violated, and then we have the solution will be inaccurate. Final solution will be inaccurate. So we have to deal with this distortion. There are many ways to deal with distortion, but when we talk about this kind of problem, all these techniques fail to address satisfactorily the kind of problem we are interested in, we are talking about. Okay, so this is another interesting example. You see, this is an example of a pipe network system. And the fluid is passing through this pipe, and then suppose there is a leak or something happened, a breakage occurs some location in the pipe. For instance, if at this point leak or that point, then what will happen? So this is the pipe, and then after the breakage, the fluid which is passing through the pipe then comes out from this leak. Okay, now what happens? Now when it comes out, then it exerts some opposite force to the pipe, right? Now sometimes the force because of this, the follower force is so high, this pipe may deform significantly. Now I can idealize this problem as this is a cantilever beam which is subjected to a force, okay? And this is the idealization of the beam. It's a cantilever beam. This G is this portion of the pipe attached to this cantilever beam, and this V0 is the follower force because of this movement, because of the fluid coming out from the pipe. Now, when we try to simulate it, you see the simulation will be this. Yeah, I mean, no, the concrete or steel structure, we do not allow this kind of deformation. Right? It is not scale deformation. This is the actual deformation that may this beam encounter, this kind of structure encounter. Now I want to simulate it. But then what happens? You see, you see these are the lines. These are some lines, thickness of the beam, and you see these lines are so this thickness lines are so severely distorted. So when you try to model it using finite element method or element-based method, because of the distortion, you may get significant problem in the computation. So these are some motivation, these are some reason why we must look beyond the classical technique and then explore the possibilities to different class of method which can be used for certain class of problem where the conventional methods cannot be used very satisfactorily. Okay. Now, before doing that, before exploring the possibilities, you see, if something goes wrong in our computer, we just don't go to the market and buy a new computer, right? We try to repair it. Okay, if we find that the computer reaches a state where repairing is not possible or repairing cost will be is huge, then only we can think of buying a new computer. So first thing always to find out a way to repair the things, repair the framework you have. For the same analogy, there is some limitation in our method in the computation framework, but instead of looking for a completely new alternative, new technique, why not try to repair the existing technique and then see whether with that repair, these methods can be adapted to this kind of problem. So there are some repair available in the literature. First, one very popular approach is to deal with element distortion in Lagrangian and Eulerian mesh. So Lagrangian Eulerian mesh is essentially I try to summarize it. This figure. What it does is it essentially changes the reference at every certain interval, so that the structure may have deformed significantly with respect to its initial configuration. But as I said, if you change your reference configuration as the structure undergoes deformation, then with the last configuration deformation may not be severe. So we will not go into the detail of this formulation. Here the idea is to let you know that there are indeed some repair available in the literature. Now another available is another difficulty in element-based methods, as I highlighted several times in the presentation, to model the fragmentation, model the crack propagation, the discontinuity that happens that the structure encounter. So in order to model that discontinuity, there is a technique available in the literature which is called XFM, extended finite element method, where which actually allow with that enrichment you can this enrichment allows your computational framework to have crack within the element, allow material separation to happen. So XFM is also quite sometime XFM has been developed. If we think some software like Abacus has a module of XFM, but then again, we are not talking about one crack or two cracks, right? We are talking about we have seen the example of a structure under blast loading, how the damage initiates, damage propagates, and then finally complete failure of the structure. So we are talking about those kind of extreme behavior. We are talking about structures under extreme loading. And when under structures under extreme loading failure, the failure mechanism includes large number of cracks, their interaction, then finally material separation, fragmentation. We are talking about those kind of behavior. Now, in those kind of behavior, XFM again may not be applicable to those kind of structure. Okay, those kind of behavior. So as of up to this, we try to convince ourselves, we try to find out the sufficient reason to look beyond the classical technique, and we found that the summary of the discussion as of now is, yes, there are certain class of problems where the conventional mesh-based methods are difficult to be implemented, difficult to be applied, and in those class of problems, we need to look beyond this conventional technique, and that is why we are doing this exercise. Okay, so that was why mesh-free method. Now let us come to what mesh-free method. What is mesh-free methods? As name suggests, the mesh-free methods. Okay, you see, the mesh-free method started long back around 70s, and we are talking about 1920, 2020. So it is almost 45 years. So over the last 40-45 years, there are several variants of mesh developed. I'll just browse through few names. These are just a very small subset of the entire set of different mesh methods available in the literature, but they are not very different from each other. They all are premised with similar kind of assumptions, and therefore in all these methods there is a common link. Now the methods are very popular and widely accepted and being used in many simulations, and some of the commercial software like Abacus and LS-DYNA, they have incorporated that method. They have in one of their modules smooth particle hydrodynamics, or it is called SPH. So we'll be talking about, we'll just highlight the different aspects of this method. Okay. So as the name suggests, mesh method is absence of mesh. There is no mesh. It is mesh free. So we have a structure like this. Say for instance, if you have a plate like this, and I have to analyze this plate using finite element method. So this is the discretization. Just giving you an example. This is the element discretization of the domain, discretization of the structure. In mesh, just remove now elements from the. So in this discretization, what we have in finite element discretization, we have the elements and the nodes. So all the elements are connected with each other at the nodes, right? Now in mesh-free discretization, we remove the elements from the system. So what we left with is just a set of nodes, set of particles. Particles is the common term used in this class of methods. So the first difference is between finite element and mesh-based and mesh-free method is, in mesh-based method, discretization through elements, but there is no elements in mesh method. It is only through particles. Giving an example in 3D, again is a 3D example of element discretization. Again, if you have to have the similar counterpart of in mesh-free, then this is a mesh-free discretization. Okay. Now, once it is discretized, now you have a structure. This structure could be a beam. This structure could be a plate. It could be a dam. It could be anything. So essentially, these structures are represented by a set of points, set of particles in three-dimensional space, right? Like this in a 3D L bracket is represented by a set of particles in three-dimensional space. Similarly, you can have representation of beam, plate, or anything. Now, one point I want to highlight here is, as I talked about when we talk about when we say it is a beam, it is a plate, it is a shell, it is a column. These are all structural idealization. There is nothing like beam, column. Nature doesn't understand what is beam, what is column, what is for nature. Everything is a three-dimensional object, right? It is for us, for our computation, for our analysis, we have given this idealization, right? Now, one important thing in mesh-free is it does not rely on those kind of idealization. Every structure now is a collection of points in three-dimensional space, right? Now, once we have discretized the structure by represent the structure by a set of points in three-dimensional space. Now, the next question comes is, then how these points or the particles, how these points interact with each other in order to have a deformation, in order to get the load transfer from one part to other part. These points must interact. Now, this interaction in mesh-free method takes place through a kernel function, but before that, takes place in finite element method. In finite element method, we defined shape function. So the shape function essentially gives you, if you have a several points within an element, and then every points you have a variable defined, then shape function allows you to find out the variable at any arbitrary point in the element. So Uy at the point could be velocity, it could be displacement, it could be stress. So Uy at the values at the nodal point, and then ux at any arbitrary point within the element can be represented like this, where ni are the safe functions. So these are safe functions for 1D case, 1D fluid case, 1D 3D case. In finite element method, we can have triangular element, quadrilateral element, Greek element. These are some examples of commonly used elements in finite element. But now we do not have element in measurement method. We have just set up particles, and these particles need to interact with each other. Now, these particles will interact with each other through a cardinal function. This is the cardinal function, a bell-shaped function. Okay, one example of this function is this. Now you see, this is the function, and these are the points, and these points will interact with each other. It is very similar to finite element method, where ui's were the values at the node, and instead of wi's, you had ni's as the safe function. In mesh-free method, ui's are the values of this particle, and wi's is the cardinal function. This is the cardinal function. And ui's give you the value of any function at any arbitrary location. Okay. So this is how any field variable, it is displacement, velocity, or any field variable can be represented. So yeah. So now in a domain you have several points in the domain. So wherever you want to have this interaction happen, you take the kernel function at that particular point. One point will interact with his neighboring points. One point will not interact with all the points within the domain. One point will interact only with the neighboring points. And this, after this neighboring point interaction happens, this kernel function. This kernel function must satisfy certain property, like safe function in finite element must satisfy some property. So, okay. These are some examples of commonly used kernel function. We can have Gaussian kernel function, we have cubic spline kernel function. We can have, this is the shape of the kernel function in 1D. The blue one is the kernel function, and the red one is the derivative of kernel function. It is kernel function in 2D. The first one is the kernel function, second one is the derivative of the kernel function. Okay. So again, you see, again, if we recall the flow in engineering analysis, physical system, then idealization, mathematical model, and the solution. Physical system we had idealization. Now in mesh-free method, every physical system is idealized by a set of points in three-dimensional space. Now once that idealization is done, the next thing is the mathematical model. What are the mathematical model? The equilibrium equations. These are the conservation equations, right? Conservation of mass, conservation of momentum, conservation of energy. Okay. The conservation of all the derivatives in conservation equation, now it can be represented by the kernel function. Same way it is represented in this element method. Okay. Now let us not go into detail of this equation. Our idea is to get an overview of this method. So finally, when you substitute all these expressions in the, so along with your conservation equation, we need a constitutive model. What is constitutive model? Constitutive model is what is the relation between stress and strain. If you apply a load on a structure, stress and strain generated, and then how the stress and strain are related to each other. So once you have this model, then finally you have to integrate over time if you are doing some dynamic simulation. Okay, so as I was saying, let us not go into the details of the detailed intricacies of the mesh-free method. The method which took several decades to develop, we do not really expect to discuss everything in 1 hour lecture, but here idea is to have an overview of this method and what kind of simulation, what kind of what is the capacity of this method, and what these methods can handle. This is with one example. This is called Taylor bullet. In fact, it's a very straightforward example. You have a cylindrical rod, and then the cylindrical rod is impacting a rigid, say, wall, and then finally, this cylindrical rod deforms like this. So the red is the simulation method, and the dots are the simulation. The reason why I showed you this, see, these simulation can be done in finite element based method, but then the we should have an understanding that for a problem where solution can be obtained from image-based method, relevant-based method, then if we apply SPH in those problems, then how the solution, what is the quality of the solution? The solution will form. Then it is just to show they match the close. Okay, now these are now onwards to that. So which actually shows the real capacity, real capability of this kind of penetration modeling. Now, if I have to give you a physical example of this problem, this is a very common problem in oil industry. You see, suppose you want to make a drill on earth, okay, earth surface, and then for some oil exploration or for any kind of exploration, in mining also this is very common. So you want to make a drill, right? Now then, suppose once you make a drill, you want some kind of trajectory. You want at what speed I send the impactor, at what speed I allow the impact to happen, so that I get certain kind of penetration. If you want that kind of information, we have to simulate it. So this is, we cannot model the entire earth surface, but what we have domain, so that this can fairly represent the earth. If you want waves generate from here, this wave doesn't get reflected from this, so it fairly represents the earth surface. Okay, so these are speed at different speed at where this penetration takes place. The first one is 1 kilometer per second. As you can see, this is the penetration. This penetration is very difficult. You cannot model using analytical. There are some simplified empirical and some analytical methods. Not analytical. The analytical is not the right word here. Some empirical formula available to the depth of penetration, and when you compare these two the results of information, you can see the fairly match. This is the problem I was talking about. I was giving an example of pipe network system. This is a very classical problem called Cox-Cantico problem, and this problem was introduced by Cox in 1950. This is almost 70 years back. But this problem is relevant because you need to at least it is a very good example of exploring different class of methods. Okay, where different class of methods. So this is the results obtained from SPH. Okay, now so we are interested in modeling cracks and then fragmentation. Now let us see how the crack and fragmentation can be modeled in SPH method. So now you have a set of particles, and every particles are interacting through kernel function. We have used a concept called pseudo spring analogy, which is developed by one of my students. Now the idea is between each particle consider a spring, and then as the particle structure undergoes deformation and the damage initiates, the spring also the damage gets accumulated at the spring. When the damage reaches a critical value, then the spring breaks, and then which is indication of there's a crack formation. The material separation has taken place. It is called pseudo spring because these springs do not contribute anything to the stiffness of the structure. It is used to only check the quality or the level of damage, and then particles interact or not to take that for pseudo spring. So you see, so these are particles connected through springs, and then some of the raised springs are broken, and then this is the series of broken spring will give you the crack path. Okay, so and this is just one example how you can calculate the damage of the spring. Damage can be defined depending on the material. It can be defined in many ways. Now, this is one way of calculate the strain at this point, and then if your criteria is strain based, which is not a very accurate criteria, but just giving an example, then damage is defined as this, and then if your this damage value reaches a critical value, which is 1 in this case, then the spring is broken. Okay, so let us see what kind of what is the capability of these methods. Now, this is again is a very commonly known cult of Winkler experiment. In 1987, it was conducted. So this is a plate. We have a crack of 50 mm depth with 50 mm crack of length, and then this is hit by a cylindrical projectile with a speed g0, and then this is the idealization of the system, and then 1/2 is model because it is met with respect to power devices. Now you see this is the dots. You can see these dots are the crack paths obtained from this, obtained from the simulation. From the experiment, it was observed the crack angle is around 70 degrees, with what is observed through simulation is around 67 degrees, which is quite consistent with the experimental observation. Okay. Now, this is another experiment done by Otis in 1999. This is a concrete beam, the supported concrete beam. We have a notch at the center, and then in this case, not with an eccentricity, and this beam is hit by an object at the next plan of beam. An object. In this case, by intuition, we can say that after the hitting, crack starts from this tip of the notch and then it propagates vertically. And in the second case, what we can, by intuition again, we can say that the crack form again from the tip, but then crack is not vertical in this case, crack will be inclined. Okay. So these are the pattern obtained from the simulation, SP simulation, as very consistent with intuition. In the first case, the crack propagates vertically, and the second case, crack is inclined, and which is again verified through experiment given in the paper by Otis. This is another experiment, the clamped beam, again hit by a projectile. Experiment done by Chain and it was aluminum beam. So you see, this is the deformed shape, not the deformed shape. It is the final deformation at different speed obtained from simulation and obtained from other analysis, and we can see that it is quite consistent. These are important. These are interesting. The first figure is the figure obtained from experiment, and the second figure, just below the first figure, below the experimental figure, is the predicted from the numerical simulation. So if there is a notch at the fixed end, cramped end, these are the deformations. Now these are the deformations, again, are quite consistent with the experimental observation, and the predicted response is very consistent with the experimental observation. But this is the box cantilever problem. But if you allow the beam to fail, then if for certain velocity, the beam can fail at the tip, and this kind of method can be used to model this failure. This is another example. This is a gravity dam. This is a Koyna dam model of a Koyna dam, and this is the Koyna earthquake data. And if you simulate the Koyna dam after this earthquake, and if we try to simulate it using SPH, and you see these are the crack pattern we observe. But again, to get this crack pattern in element-based method, you have to do a lot of additional things like enrichment with XFM. But then sometimes with those enrichment things, it becomes very difficult to model interaction of cracks when the number of cracks are very large. But in this method, these methods are naturally equipped to deal with or handle this kind of situation. Okay, so let us then finally summarize what we have discussed. As I started with what is this? So idealization is one of the important in any engineering analysis. If you see the physical system, then idealized system, mathematical model, and the solution. Idealization, representation of mathematical to a mathematical model, and simulation. We call together that is structural analysis. Now, this analysis, the framework, analysis framework, there is nothing like which is correct framework, which is wrong framework, as long as it is mathematically consistent. But the question we should ask is, for a given problem, whether that framework is useful or not. Then we argued the kind of problem we are talking about. There is some class of problem like the structures under extreme loading, when the structure undergoes severe deformation, and then the severe damage, crack propagation and interaction, material settling. If you're talking about those class of problems, then again, some of the methods which are very, very well known, widespread, name a field, whether in engineering or science or some other field, there is an application of element-based method. But then again, even in all these, there are a very small set of problems where those methods, the application of those methods are very, very difficult. And in those problems, in those class of problems, we need to look beyond the classical technique, modeling technique. And when we look beyond, we find there is a class of method which is known as mesh-free method. And these mesh-free methods has a potential to deal with this kind of behavior. There are many variants of mesh-free methods developed over the last 4 decades, but the method which is most popular and is used in many cases, and it is included in some of the commercial software, in smooth particle hydrodynamics. It's a very popular. It is not just popular in structural engineering. It is popular in computational fluid dynamics. It started with problems in astrophysics and then adapted in fluid dynamics problem, and then of late it is being explored in structural dynamics problem as well. So this method has a potential. We try to understand the capability of this. We try to browse through the different features of this method, and through that process, we try to understand what is the capability of this method. Okay. Now, so, but then there is a saying: there is nothing. There is nothing like free lunch. Nothing is free. If there is some advantage of this method, there are some limitations of the method. The limitations are related to some of the methods are found to become unstable in certain circumstances, and some of the methods are found to be inconsistent in certain circumstances. But then when you develop a computational framework, keep that in mind. The point here I like end with that message that don't look at this method, this speech, or all other the name I mentioned. Don't look at them as a method. Rather, we must look at them as a concept. And what is the concept? The concept is remove elements from the system, allow particles to interact. How you allow, you decide yourself based on the stability, consistency, what kind of problem you are talking about, you are dealing with, and develop a computational framework. Okay. And if we can develop a computational framework with that concept, and this framework indeed has potential to deal with this class of problem. With this, I stop here. Thank you for your patience, and if you have any questions or any discussion, it would be nice.
Thank you so much, Dr. Amit Shaw. It was very interesting. In fact, I think you have taken up a new concept. Rather than using elements, why not use particles for analysis? Does it increase the accuracy or something like that as compared to finite element and methods?
No, I mean, you see, the first of all, the comparison with finite element method won't be fair. The reason I'm saying so, because our target problem is those problems where finite element method has a difficulty to be implemented, right?
Okay.
But as far as accuracy, it has been validated through experiment. Yeah, it has been validated through experiments that the prediction from these methods you get, they are very consistent with the experimental observation.
Any software, this thing which is using this mesh-free method?
Yes. LS-DYNA has a module of SPH, and then Abacus has a module of SPH that recently included. Not recently, it is quite a few years now. They have included some modules. In fact, I'll tell you, now there is a concept, not now, it's quite old again, the hybrid method. Hybrid method means the last example I was showing, the simulated in
the
last one, that was it was a hybrid technique we used. Hybrid technique is you start with finite element method, okay, do the simulation with finite element method, but then if you find during the simulation that some elements are getting distorted, there is some damage or some fragmentation, you remove those elements and replace them by some particle. So it is a finite element method and particle based method combining both.
That is a very one more question that is being one more question that is being asked is, how is it practically checked after modeling the structures? Does the equation change for every model that is analyzed?
Equation. I mean, equation. What equation you use, that that depends on what kind of simulation. For instance, suppose you want to model a structure under fire. Suppose I'm giving just an example. Then of course you have to consider the heat part in your equation. So equation depends on what kind of, and that is true even for finite element method. So what equation you use, what equation you use, that equation depends on what kind of, it doesn't depend on the structure, it depends on what solution, what are the components you have in the analysis, you want to put in the analysis.
So I think that's a very fair thing, because we need to understand what are the components that is being analyzed, and then maybe we go for one or the other method or a hybrid method. I mean, that has to be analyzed.
Exactly.
That is.
So
this is one of the.
In automobile industry, they do these crash analysis of vehicles. They do real tests, but how many times you do the real test? You have to simulate what safety features in a vehicle. So you need to do crash analysis, right? Now, when you do crash analysis, many places they use this hybrid method. So you have the entire vehicle method, and then after the hit, as the elements are getting deformed, distorted, damaged, you replace through elements. You replace by particles.
Is the mesh-free method used by designers in the construction companies and all nowadays? Are they using it? Is there any practical?
Not really. It is again for
analysis.
Specific. For analysis, yes. Suppose, as I said, for specific kind of structures about to design for military application. Okay, I want to design an armor for vehicle. I want to design, say, a structure which is subjected to blast. I want to design a structure which is subjected to impact. So those I want to analyze, say, power plant, some nuclear power plant. So some of the important structures where the circumstances are also very severe, under extreme loading. In those cases, yes, we do use mesh-free.
Mesh-free.
Yes.
That means, I think what you're saying is that wherever there is a sudden impact, maybe for the earthquake also, is it applicable for earthquake also?
Yes. The last example I showed you, it is the corner dam subject to earthquake, and then you want to study how the crack forms and the failure of the dam. Yes, you can use mesh-free. So wherever there is a major problem area is wherever
impact.
Not just impact. If there is a failure of structure by crack formation, interaction of crack, damage, separation, in those class of problems, you these methods are very well equipped to handle.
I think for the study of failure mechanism, I think it is very much useful, especially for those areas where it is prone to disasters and all that. Exactly. I think this method can play a very vital role.
Exactly. Then
so thank you so much.
Just to give you another important area where it is being explored is a fluid structure interaction problem. Okay, suppose you want to study the behavior of sheep under wave load. Okay, so sheep and then wells. Okay, so you model using finite element method, or if you are using sheep as a rigid body, model the entire fluid using particle-based method and get the interaction. So fluid structure interaction problem, these methods are being explored.
Okay, wherever fluid is involved, I think probably particles would be much more logical. Exactly. That's what you are saying, is it? Like.
Yes, exactly.
So this is a very good example of ship and fluid, where the fluid can be designed as mesh free, and maybe the ship can be designed as a PM or something like that.
Exactly.
Yeah, that's very interesting. So I think it throws one more this thing on how we can analyze it. Using so many methods are available nowadays, and mesh free is one of the methods which it can be used.
Yes.
So thank you so much, Dr. Amit Shaw, for sharing your information with us. It was nice talking to you. And I'm sure that so there are few professionals who may not be able to log in now. I think they would be seeing it in the evening or something, because we have a YouTube as well as an FB Live. So in case there are any questions, further questions of clarification, we may be sending you by email. So thank you for joining us. So thanks all the professionals who have joined us and taken up their time.
Very much.
Thank you so much. Thank you. Stay safe. All the best.
Yeah, you too.
Thank you.